Good morning, myself Amma Rakshaya. I'm from CSIT branch. Today my AAT concept subject is theory of computation and topic is Turing machine and definition and model. Introduction. A Turing machine is an accepting device that accepts the languages recursively generated by type O grammars, that is recursively enumerable set. It was invented in 1936 by Alan Turing. A Turing machine, TM, is a mathematical model which consists of an infinite length tape divided into cells on which input is given. It consists of a head which reads the input tape. A state register stores the state of the Turing machine. After reading an input symbol, it is replaced with another symbol. Its internal state is changed and it's moving from one cell to the right or left. If the TM reaches the final state, the input string is accepted, otherwise rejected. Definition. A Turing machine can be formally described as a 7-tuple where Q is a finite set of states, X is a tape alphabet, delta is the input alphabet, lambda is the transition functions, that is Q and X implies Q and X, that is shift left shift and right shift. Q naught is the initial state, D is the blank symbol, and F is the set of final states. Comparison with the previous automata. The following table shows a comparison of how a Turing machine differs from the finite automata and pushed out automata. First, finite automata in stack data structures, it is normal automata and deterministic, and yes, it is. Pushed down automata, it is a last in first out format and it is not a deterministic. Turing machine, it has a finite tape stack data structure, and yes, it is a deterministic structure. Example of Turing machine. Example of Turing machine where Q is equals to Q naught, Q1, Q2, and QF states. X is equals to A comma B, where Q naught is equals to Q naught, and B is a blank symbol, and F is equals to QF, and delta is equals to 1. Tape alphabet symbol and present state is Q naught and present state is Q1, present state is Q2. There we have 3 states. With the type alphabet, tape alphabet A, the present state of Q naught is 1 into R into Q1. In the present state Q1, 1 left Q naught. In the present state Q2, 1 left QF. In B tape alphabet symbol, present state Q naught, 1 left Q2. For present state Q1, 1 R Q1. For the present state Q2, 1 R QF. Here the transition of 1 R Q1 implies that the right symbol is 1. The tape moves right and the next state is Q1. Similarly, the transition 1 left Q2 implies that the right symbol is 1, the tape moves left and the next state is Q2. That is followed for all the tape A and B alphabet symbols for the present state Q naught, Q1, and Q2. Time and space complexity of the Turing machine. For a Turing machine, the time complexity refers to the measure of the number of times the tape moves when the machine is initiated for some input symbols, and the space complexity is the number of cells of the tape written. Time complexity, all reasonable functions, that is T of n is equals to big O of n log n, and space complexity of Turing machines is S of n is equals to big O of n. Designing a Turing machine. A Turing machine accepts a language if it enters into a final state for any input string W. A language is recursively enumerable generated by type O grammar. If it is accepted by a Turing machine decides a language if it accepts, it refers into a rejecting Turing machine. Recursively, it is decided by a Turing machine. There may be some cases where Turing machine does not stop. Such Turing machine accepts the language but is not decided. The basic guidance of designing a Turing machine have been explained below with the help of a couple of examples. For example, design a Turing machine to recognize all strings consisting of an odd number of alphas. So let the Q1 be the initial state. If M is in Q1, on scanning alpha, it enters the state Q2. For M is in Q2, on scanning alpha, it enters the state Q1 and writes B. From the above moves, we can see that the M enters the state Q1 if it scans an even number of alphas, and it enters the state Q2 if it scans an odd number of alphas. Hence, Q2 is only accepting state. Here, M is equals to Q1, Q2, 1 comma B alpha, and Q1, B, Q2, where alpha is given by tape alphabet symbol, and present state Q1 is BRQ2 and present state Q2 is BRQ1. Turing machine model. Turing machine can be modeled with the help of the following representation. The input tape is having an infinite number of cells, each cell containing one input symbol, and thus the input string can be placed on tape. The empty tape is filled by a blank characteristics. The finite control and the tape head, which is responsible for heading the current input symbol, the tape head can move to left to right. A finite set of states through which machine has to undergo. Finite set of symbols called external symbols, which are used in building the logic of Turing machine. Here is a model of Turing machine where we can see an input tape and a tape head on the right of the diagram. And for the input, we have a finite control. Chomsky hierarchy. Chomsky hierarchy represents the class of languages that are accepted by a different machine. The category of language in Chomsky hierarchy is as given below. Type 0 known as unrestricted grammar, type 1 known as context sensitive grammar, type 2 known as context free grammar, and type 3, that is fourth one, is a regular grammar. Here we can see the Chomsky hierarchy. The first is unrestricted grammar type 0 and context sensitive grammar type 1, context free grammar type 2, and regular grammar, the last one, and the inner circle is the type 3. This is a hierarchy, therefore every language of type 3 is also a type 2, 1, and 0. Similarly, every language of type 2 is also a type of 1 and type 0, and etc. Type 0 grammar. Type 0 grammar is known as unrestricted grammar. There is no restriction on the grammar rules of these types of languages. These languages can be effectively modeled by Turing machines. Example, small b, capital A, and small a, that is implies small a and A, and capital S implies S. In type 1 grammar is known as a context-sensitive grammar. The context-sensitive grammar is used to represent context-sensitive language. The context-sensitive grammar follows the following rules. The context-sensitive grammar may have more than one symbol on the left-hand side of their production rules. The number of symbols on the left-hand side must not exceed the number of symbols on the right-hand side. The rule of the form A lambda is not allowed unless A is a start symbol. It does not occur on the right-hand side of any rule. The type 1 grammar should be type 0. In type 1, production is in the form of V implies T, where the count of the symbol in V is less than or equal to T. Here is an example, that is the first S implies A, T, where T implies X and Y, where A implies A. Type 2 grammar. Type 2 grammar is known as a context-free grammar. Context-free languages are the languages which can be represented by a context-free grammar, that is CFG. Type 2 should be type 1. The production rule is of the form as follows, that is A implies alpha, where A is any single non-terminal and is any combination of terminals and non-terminals. Example, A implies small a, capital B, and small b. The second one, capital A implies small b and capital B implies small a. Type 3 grammar. Type 3 grammar is known as regular grammar. Regular languages are those languages which can be described using regular expressions. These languages can be modeled by NFA or DFA. Type 3 is most restricted form of the grammar. The type 3 grammar should be type 2 and type 1, and type 3 should be is of the form V implies T into V by T star. Example, capital A implies small x and y. Thank you.